Hello everyone, welcome to my second OpenGL demonstration. We're going to pick up where we left off last time. There's been a fair few changes to the OpenGL framework since we last talked, so we're going to look at some of those as well. And let's get right into it. This was lesson number 5 that we looked at last time. Let's close that away. We're now fairly open cross-platform compatible. We've got Linux, Mac and Windows. The Windows and Mac interfaces include both Windows and Pixmap. Linux does include Pixmap, but it's a bit buggy right now. But that won't matter so much depending on what you're trying to do with OpenGL, and we'll talk about that in a second. So let's get started here. There was a call last time on my blog for a demonstration of transparency. So let's jump ahead to lesson number 8, which is a lesson on transparency. Here we have a stained glass window and we rotate it around. This is a Nihi lesson, and the Nihi lesson demonstrates how to use blending. Now, blending in OpenGL is special. I really recommend if you want to do blending in OpenGL, you have to go read some books and some online materials. Blending in OpenGL is quite tricky. It's generally used to do things like fire effects and stained glass windows and things like that, or high definition rendering and stuff like that. It's not a normal rendering technique in OpenGL, simply because you have to, as a programmer, draw the transparent texture maps last, which means you have to be quite aware of what's going on in your scene, and it can be quite tricky. The reason you have to do it last is because it projects the pixels through to the things behind it to see what's actually behind it and what it needs to draw, and it needs to do that once the buffered scene is actually set up. So that's just a limitation of 3D cards. It's because they're not real ray tracers, they're fake ray tracers. Anyway, that's an example of blending, and let's have a look at the code behind that. So first thing we do is we go and make ourselves a bitmap that includes our image, and this is the glass image from our lessons. We turn on our lighting so that we get cool lighting effects, and we turn on blending. So as soon as you turn on blending, the world of 3D goes wacky. When we render, we don't have to do anything special except make sure that all the textures are blended so that we get a uniform blending effect, and we're just drawing a cube here with textures mapped onto it. And that's it. That's the transparency. Okay, fonts. So last time we looked, we only had fonts available for Windows. Now we have fonts available for Linux, Windows, and Mac. We only have bitmap fonts available on all three platforms. The fancy fonts, the vector fonts, only exist for Windows. It's possible to do them on Mac, but I'm not interested in doing that right now because you generally only want to use the bitmap fonts anyway. So, fonts, how do you use them? You create yourself a font description, you use the font description with the font policy to create a font, and then you go new font list on the context. That's as simple as that. Then when you want to render, you go display string with a font. And that's it. There's the string that you want to display. You can use raster position to get the coordinate position of the text that's going to be displayed set in a two-dimensional fashion on a 3D screen, and that's all there is to it. This gives us, I'm running on Mac OS here, OS X here, TrueType fonts rendered in OpenGL. Voila. One of the really cool things that you can do in OpenGL is jump straight ahead to models. So models can be very complex. There's a program called Milkshape 3D, so I'll highlight here, which can import and export lots and lots and lots of different 3D model formats like 3ds Studio, Half-Life 2 models, Quake 3 models, so on and so forth. It does lots of models, but it's also got its own format, which is a minimum vector format, and it's reasonably easy to parse and read and interpret for ourselves. So I have a package here called Milkshape 3D, which does just that. It creates a model which contains meshes and materials. The meshes contain triangles, and the triangles contain vertices. Now, this information can contain information about textures as well, and that's really all there is to it. You need to use their editor to actually build these files. I think down the track one day it might make sense to make our own sort of model engine here in Smalltalk, because every game ends up making its own model engine one way or another anyway, because it wants to store different information in different ways, and everyone thinks they can do it better than everyone else, which is in many respects sometimes true. The ultimate modeling format is actually to create vector buffers, and vector buffer arrays can be sent directly to the video card, and it's the most efficient way to do it. Essentially, when we do OpenGL commands and we say, okay, here's a vertex, here's a color, etc., we're creating a vertex buffer array. And by doing those commands, when we hit the end, the vertex buffer array is built and sent to the video card. So by using vertex buffer arrays, which are pre-configured, pre-calculated things, you avoid having to do all these OpenGL commands to do the same thing. The end result, though, is this demo here, which is the NIHI Lesson 31 demo, which is a model of a cross that contains textures on it, and it's just rotating around there. The reason we're looking at it slightly down is because we're using the lookat command. The lookat command is kind of neat. Let's have a look at the lookat command. So look from, give it a coordinate in space, to where you want to look at. Now, normally when you're doing rendering, you always look at 0, 0, 0, and you use translate to move somewhere else, and you're always looking back at 0, 0, 0, which is interesting. But look from lets you look at anything you want with any up orientation you want. So if we want to change the orientation, so we look at this thing upside down, we can make that -1, and now we're looking at it upside down. So this is, again, an example where we just changed the code, the program recompiled, and the running program updated. I've got an alternative demo here that shows a more complex model, one that clearly needs lots of CPU time to actually do properly. It's got curved surfaces, curved joints, multiple colors, reflectiveness, all kinds of interesting properties here. It's even got like a window here. This is a TIE Defender from Star Wars. Somebody put this out in open source, and I converted it with Milkshape 3D, and here we have it in one of our demos. And now let's have a look at what our frames per second is and see how we're going. So press question mark there, and it dumps out the information here. We've done 693 iterations at 30 Hertz. We've dropped 0 of them. Our render time is 1 millisecond. So this is Smalltalk doing all this stuff here, and we discovered that we're not actually spending much time doing things at all. And our effective frames per second here is 732 frames per second. Now, if you did a full tight loop rendering, you wouldn't get that speed because you'd be generating lots of garbage, and the VM would have to slow itself down and clean up that garbage. You really don't want to do that anyway, because when you do games development, you need time for network latency and all that kind of stuff. So we'll talk about immediate mode graphics in just a second. So the free time, we actually had 31.9 milliseconds of free time on average out of the 30 Hertz, which is about 33 milliseconds every second. And the physics time, which is doing the rotation, was immeasurable. It's so small. When you start doing more interesting physics, then obviously that time goes up. But as we note here, we have a lot of free time to play around with. Even drawing a complex scene usually only gets up to 10 milliseconds of render time. Then you've got another 23 milliseconds to do your networking and physics and events and all that kind of stuff. We'll see more of that in a second. Okay, one other thing you really need to be able to do when you're in OpenGL mode in 3D is to draw in 2D. And ironically, it's actually pretty hard to do. So here is an example of something with blending and lighting. So we've got these two triangles here, they blend together, they've got lighting, they've got edges, they're rotating in 3D, and over the top of that, we've drawn two two-dimensional boxes to demonstrate that we have complete control over the area of the screen that we're working in. So let's have a look at how this works. Our renderon is doing render the 3D scene, render the 2D scene. It's important to render the 3D scene first because generally the 2D scene is what you're going to be rendering as, I don't know, widgets and statistics and health bars and all that kind of stuff. So you want that on top anyway. Render 3D sets up a perspective mode like you normally would, turns on lighting, and renders the triangles. Nothing too special there. Drawing the 2D mode changes the perspective. It goes back to the projection matrix mode, sets up an orthogonal view for our bounds. It goes back to model matrix view, disables the blending and the lights because we can't use them in this anyway, and then draws the two boxes. Now, when you're in 2D mode, 0, 0, 0 is the flat plane. The bottom left-hand corner of the screen down here is 0, 0, and the top is your bounds extent, the top right. This is different to 2D rendering where the top left is here and the bottom right is down here. So we're now dealing with a real coordinate system, mathematically speaking, where we project outwards like this. This is the y coordinate plus, x coordinate plus, and backwards is z coordinate plus. So what we do is we want to move backwards by 1. So we move back through the z coordinate -1 so that we're looking at the screen from 1 pixel away or 1 point away. And that means we can actually see the 2D scene. And that's how you do 2D drawing. Now, the OpenGL library itself has changed a bit since we last looked at it. We still have our OpenGL interface, but because we split out into different platforms, only OpenGL lives in here now, and OpenGLU, because GLU is basically part of OpenGL anyway. So There's also a special constant in the OpenGL namespace. So when you're programming, you generally want to import the OpenGL namespace. Or if you're working in a workspace, you don't have to do anything. It just works. It's imported by default. So you can call GL and you can do any kind of GL command you would normally want to do. All of the constants in OpenGL are also in here. So you don't have to specifically call a method to get a constant. You can just say GL1. To see what I mean by that, if we look at the OpenGL context, which is the guy that makes everything easy, here's the clear command on context, where you just go context clear. It does it the C way. It goes GL clear, GL color buffer bit, or GL depth buffer bit. So instead of having to write this amount of code all the time, we can now just go context clear. And you see this kind of code all the time. So the OpenGL context, which is the thing you see in the lessons all the time, is provided to you by the OpenGL component OpenGL window in the renderon method, which is renderon, gives us a context and we can draw whatever we want. And renderon gives us a context and we can draw whatever we want. So we now have two different ways of drawing OpenGL. We have the OpenGL component and OpenGL window. I'm going to start with the OpenGL component and then go back to OpenGL window because there's some interesting background stuff you need to know to understand what's really going on here. OpenGL component is a reusable visual component in the VisualWorks wrapper GUI framework, which means it's a reusable widget. You can drop it inside a screen and draw some OpenGL scene and away you go. However, there is a limitation. Here is an example of doing exactly that. This is an OpenGL example, which contains an OpenGL rendered section and two buttons, a button up the top and a button down the bottom. You may have noticed it took a little while to come up. The reason it did that is because we're running this window in double buffer mode. There is no easy way to share a bit-blitted Windows buffer with OpenGL and have everything work correctly. The reason for that is that OpenGL always runs in RGBA. VisualWorks always runs in BGRA or ABGR, and that's alpha blue green red instead of red green blue alpha. They're the opposites of each other. More than that, OpenGL actually runs in top to bottom Y coordinates, but on Windows, when you've got a device independent bitmap, it actually runs upside down. Device independent bitmaps on Windows go from the bottom to the top, so images are always upside down. So on the different platforms, you've got all kinds of different barriers to making this run fast. So I've opted for the simplest solution right now. Instead of trying to figure out P buffers, you can use OpenGL component, just don't expect to get a high frame rate out of it. So if you want to render a 3D scene based on parameters, etc., and actually have OpenGL in your window, you can do that. If you want real speed out of it, you have to use OpenGL window. Okay, OpenGL window is an immediate mode OpenGL window. What do I mean by immediate mode? Immediate mode is the opposite of modern widget systems. And I guess modern isn't kind of derogative towards immediate mode. Immediate mode is pretty much how all games are made. The idea of immediate mode is that you have a render loop, we actually have a game loop. And the game loop will do physics, rendering, networking, events, one by one. It'll do it sequentially, and it'll do it in a period of time, wait a bit, and then repeat. This is a polling sort of approach, but more importantly, in non-immediate mode graphics, you build up widgets and you keep those widgets around. You keep the state of a widget around, and it knows where it's going to be on the screen, and you can do an invalidate and redraw only a bit of the screen. In immediate mode graphics, you don't make the assumption that you have a widget hierarchy at all. You don't build up a hierarchy. You have your program, which will render your scene, and you have your events, which will handle the events, and it's all kind of breadth first instead of depth first programming. And this is generally the way games are made. So if you don't understand immediate mode graphics just yet, maybe you'll get it in a little bit of time, and you might like it, you might not. And it doesn't really matter because you can use immediate mode to make non-immediate mode graphics anyway. So immediate mode means that we don't use invalidation at all. What we have is a render loop, and the render loop is provided by execution loop. Execution loop is our immediate mode driver. You give it a thing you want to do and a block to do it with. So testing, testing 2. If we run this example, we'll see it go testing, testing 2, testing, testing 2 as fast as it can at 30 Hertz, which is configurable, and then tell us the statistics at the end. So if we run that, we see 1, 2, 1, 2, 1, 2, 1, 2 spilled out, and we get 19 iterations at 30 Hertz. We dropped 9 iterations because of the speed of the transcript printing while recording the movie, and we end up with split time for the actual execution. So what does that mean for the actual rendering engines? In the OpenGL window, in initialize, we create an execution loop. We have render, which does our render, and we have physics, which does our physics. And we'll see an extended version of that in a moment. So the render loop will run at 30 Hz per second, drawing every time, and we can see from that that we should be able to get some statistics on speed. So if we come back down to our model, this is the cross model. Okay, it's spinning around. We hit question mark, we get our statistics out. And we see that we're getting a render time of 2 milliseconds, which is 452 frames per second. Free time, we've got 31 milliseconds, which is quite high. And we've got no dropped iterations. The physics is just doing rotation. It's too fast to calculate. The alternative one, the less than 31 alternative with the tie defender, is a much more complex model. But it's also going to be fast because we use a calling list. So if we clear that and do question mark again, we see we get the same statistics, 483 frames per second, render time 1 millisecond, average 2 milliseconds. And that's pretty common for rendering. More complex scenes can get up to 10 milliseconds. And the only way you can really make it slow is to not use calling lists, which you shouldn't do. Now, if you want to make a game, you've got one more problem. The VisualWorks VM provides a platform-independent keyboard interface. And because it's platform-independent, it behaves the same on every platform. Every platform does keyboards a little bit differently. For example, on Windows, when you get keyboard repeats, you actually get an event of down, up, down, up, down, up, down, up, which is not really what you want. On Mac, the keyboard interface from the VM doesn't give you the differentiator between left control and right control, left alt, right alt, left command, right alt command, and you can't get at keys like function and multimedia keys in general. So the platform independent keyboard interface is great for building regular applications, but when you want to hit the games, you really want more control. And more importantly, you want an immediate mode interface. In other words, you actually want a polling keyboard. You don't want to have events coming in randomly and having to process them during the middle of a network or render. You only want to process events during the period that you're doing the events processing in your execution loop. So you actually want a keyboard that polls. You want to be able to say update keyboard and have it then fire all the changes between what it was like before and what it's like now. On Windows, we do this by using get keyboard state, which gives us a copy of the keyboard as it is. And on Windows, on Mac, we use get keys, which does the same as on Windows and gives us a copy of the keyboard state. When we want to use this thing, I have an example application down here that I'm building up into a game one day. In my initialize method, I add two new things to the loop. Events, so we're going to now do events, and network, where we go and do our networking. In events, we simply tell the keyboard to update if we are the active window. What that means is it will then go and compare the old state of the keyboard to the new state of the keyboard and fire some events. And the events that it's going to fire are these ones. We've said on up, escape key, close the program. On up K, initialize the keyboard again so we can modify it while we're running. On up F, show the execution loop statistics. Then we've got minus and equals. So now that we're talking to the operating system more directly, we're talking about the keyboard layout, not keys in terms of ASCII keys. So there's no differentiator between an uppercase letter and a lowercase letter. You only have the uppercase letter and you have the shift key. So you can see, okay, the shift was on and the uppercase A character was pressed, which means uppercase A. If the shift was off, then it means lowercase a. So here we have the equals key. What I really want is the plus key in terms of zooming in and out, minus and plus. But we're actually hitting the equals key. We don't want shift down. We don't really care if shift's down or not. So that zooms us in and out. And then we've got left, down, right, and up to move the ship around. Okay, so what does this little demo look like? Here we have our thing. We can hit minus and zoom out, equals and we zoom in. Now, we have a distinct kind of responsiveness to the environment now. It's because of the execution loop, immediate mode graphics, and the fact that we're getting keys directly from the operating system. And basically, we're cutting out a lot of the middleman. Okay, so we zoom out, and we're facing 0, which probably means to the right. We press forward and we start moving. We can see we're moving away from the other cube. We can turn around, fly back, and fly around a bit, like so. So this is nice and smooth. This is what you'd expect from some sort of game. And just zooming out a bit more because it's very easy to get lost. Let's come in here and sort of stop. Okay, so let's get the frames per second statistics out here. And we see that our physics time still doesn't measure, our render time is still really quite low. Our event time, which is our keyboard event handler, is measurable but really minuscule. Very high frame rates per second, and we still got lots of free time. So, and this means that I can add in another part of the execution loop for AI, NPC characters, etc. I can hook up the network behavior and actually have the network communication happening, and that's it. That's how you put together a game in Visualworks using OpenGL. Cheers.